Imagine a light so blinding, so utterly powerful, that it outshines an entire galaxy. Not just a little brighter, but hundreds, even thousands of times more luminous than all the billions of stars combined. This isn't the glow of a single sun or a nebula's gentle haze. This is the furious, incandescent roar of a quasar, the universe's most extreme beacons. From our vantage point on Earth, these objects appear as mere pinpricks of light, often indistinguishable from distant stars. Yet, the reality is far more dramatic. A quasar is not a star at all, but the hyperactive, incandescent heart of a galaxy, powered by a monstrous black hole actively consuming matter. They are the universe's most luminous objects, capable of radiating more energy in a single second than our sun will in its entire 10 billion-year lifetime. They are ancient, often observed at the very edge of the observable universe, remnants of an era when galaxies were young and violent. Their existence challenges our understanding of gravity, energy, and the very evolution of cosmic structures. What are these cosmic powerhouses, and how do they achieve such mind-boggling luminosity? Prepare to journey to the edge of the cosmos to find out. The story of quasars begins not with their light, but with their very existence as a mystery. In the early days of radio astronomy, specifically the 1950s and 60s, astronomers began detecting incredibly strong radio sources scattered across the sky. When they tried to pinpoint these sources optically, they found faint, star-like objects. But their spectra were bizarre. The spectral lines, which indicate the chemical composition and motion of celestial bodies, were shifted far more than expected for any known stellar object. These shifts suggested immense velocities, far too high to be explained by stars within our own galaxy. Some of these objects were identified as quasi-stellar radio sources, hence the name quasar. The puzzle was, how could something that looked like a star but was emitting powerful radio waves and exhibiting extreme spectral shifts exist? It implied these objects were either incredibly energetic or incredibly distant, or perhaps both. The breakthrough came when astronomers realized these quasars were likely located at cosmological distances, meaning they were billions of light-years away. This realization meant their apparent faintness was due to distance, and their sheer luminosity must be astronomical to be visible at all. The energy output required was unprecedented, far beyond anything a single star or even a cluster of stars could produce. The central engine of a quasar is now understood to be a supermassive black hole, residing at the core of a galaxy. These are not the stellar mass black holes formed from the collapse of individual stars, but behemoths millions to billions of times the mass of our Sun. Imagine a gravitational maw so vast it could swallow our entire solar system many times over. But a black hole itself is invisible, a singularity from which not even light can escape. So, how does it produce such brilliant light? The answer lies in the material around it. As gas, dust, and even stars fall towards the supermassive black hole, they don't just plunge in. Instead, they form an accretion disk, a swirling, flattened vortex of matter spiraling inwards. This disk is not empty space. It's densely packed with particles moving at incredible speeds, often a significant fraction of the speed of light. The friction between these particles, compressed and accelerated by the intense gravity, heats the disk to millions, even billions of degrees Celsius. This superheated plasma glows with an intensity that dwarfs anything else in the cosmos. It emits across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays, but its peak brilliance is often in the visible and ultraviolet light we can detect. The sheer scale of energy produced by quasars is difficult to comprehend. Take the most luminous quasars, like 3C273, the first identified. It's estimated to be around 1,000 times more luminous than the entire Milky Way galaxy. This means it's radiating energy at a rate of approximately 10 joule, 41 watts. For comparison, our Sun outputs about 3.88 10^26 watts. To match the luminosity of a bright quasar, you would need about 100 trillion suns. The efficiency of this energy production is also remarkable. While nuclear fusion, the process powering stars, is only about 0.7% efficient at converting mass to energy, the gravitational energy conversion in an accretion disk around a black hole can reach efficiencies of 10 to 40%. This means that for every kilogram of matter that falls into the black hole, an enormous amount of energy is released. This process is so efficient that it can sustain the immense radiation output observed from quasars for millions or even billions of years. The fuel for this process comes from the surrounding galactic environment, gas clouds, stars pulled too close, and material from galactic mergers. Quasars are not just fascinating objects in their own right. They are invaluable tools for understanding the early universe. Because they are so luminous, they can be seen across vast cosmological distances. The light from the most distant quasars has traveled for billions of years to reach us, offering a glimpse into the universe as it was when it was much younger, perhaps only a few 100 million years old. This era, known as the Epoch of Rhyonisation, is a critical period when the first stars and galaxies began to form, and the neutral hydrogen gas that filled the early universe was ionized by this new radiation. By studying the light from quasars as it passes through the intervening intergalactic medium, astronomers can analyze the absorption lines imprinted on the spectrum. These absorption lines act like a cosmic barcode, revealing the composition, temperature, and density of the gas clouds the light has traversed. This allows scientists to map the distribution of matter, study the formation of the first large-scale structures, and understand how the universe transitioned from a dark, neutral state to the transparent, ionized state we see today. Quasars are essentially cosmic lighthouses, illuminating the path of cosmic evolution. The phenomenon of quasars also plays a crucial role in galaxy evolution. The intense radiation and powerful jets emanating from the central black hole can have a profound impact on their host galaxies. This is known as AGN feedback, where the active galactic nucleus, AGN, the quasar being a particularly luminous type of AGN, influences the surrounding gas. The outflow of energy can heat up or expel gas from the galaxy, quenching star formation. This means the quasar can effectively shut down the birth of new stars within its galaxy. This feedback mechanism is thought to be vital in regulating the growth of galaxies and the size of their central black holes. Without this self-regulation, galaxies might continue to grow unchecked, leading to the formation of much larger structures than we observe. The relationship between the mass of the central black hole and the properties of the host galaxy, such as the bulge mass and stellar velocity dispersion, suggests a co-evolutionary process. The quasar's activity is not just a passive emission, it's an active participant in shaping the galaxy it inhabits. One of the most dramatic features associated with some quasars are relativistic jets. These are powerful, collimated beams of plasma and charged particles that are ejected from the vicinity of the supermassive black hole at speeds approaching the speed of light. These jets can extend for hundreds of thousands, even millions of light years, far beyond the confines of the host galaxy itself. The exact mechanism by which these jets are launched is still an area of active research, but it's believed to involve the twisting of magnetic field lines within the accretion disk and around the black hole's ergosphere. These jets are not just spectacular displays, they are significant sources of energy in the universe. They can heat the intergalactic medium, influence the distribution of matter, and even trigger or suppress star formation in other galaxies through shock waves. When these jets are pointed towards Earth, we observe them as blazars, a particularly intense type of active galactic nucleus where we are looking directly down the muzzle of the jet, making them appear even brighter and more variable. The study of quasars has evolved dramatically with technological advancements. Early radio telescopes provided the first clues, but it was optical telescopes that confirmed their quasi-stellar appearance. The development of spectroscopy was crucial for understanding their immense distances and powerful engines. More recently, space-based observatories like the Hubble Space Telescope and the James Webb Space Telescope, JWST, have revolutionized our view. Hubble has provided stunning optical and ultraviolet images, allowing astronomers to study the host galaxies of some closer quasars and to resolve finer details in their structure. JWST, with its infrared capabilities, is particularly adept at peering through dust and gas that can obscure optical light, and at observing the most distant objects. JWST can capture the faint light from the earliest quasars, pushing the observational frontier back to just a few 100 million years after the Big Bang. These instruments, along with advanced radio arrays like the Atacama Large Millimeter, Sub-Millimeter Array, Altri ALIME, allow us to probe the physics of accretion disks, the launching of jets, and the intergalactic medium with unprecedented precision. Each new observation adds a piece to the puzzle of how these cosmic giants form and evolve. Quasars represent some of the most extreme environments in the universe. They are powered by the gravitational might of supermassive black holes, transforming matter into light with astonishing efficiency. They act as cosmic archaeologists, revealing secrets of the early universe, and as galactic sculptors, shaping the evolution of their host galaxies. From faint radio signals to blinding cosmic lighthouses, their journey from mystery to understood phenomenon is a testament to human curiosity and scientific endeavor. While we have learned much, the precise mechanisms of jet formation, the detailed interplay between quasars and their galactic environments, and the full census of these objects throughout cosmic history remain active areas of research. The ongoing exploration of these distant, luminous giants continues to push the boundaries of our understanding, reminding us of the vast, dynamic, and